If you would recall, this is the situation that we found ourselves in yesterday. After reminding ourselves about how polar coordinates work, we have this new way of describing two-dimensional space, which means we have a new way that we want to set up double integrals. Remember that setting up a double integral, the big challenge is describing the values you want to plug into your function. We simplified this to think about what's x between and what's y between. I did that backwards with the hand gestures. What's x between and what's y between. Then we thought of that as being in a small area. We said, here's a chunk of x, here's a chunk of y, and then we'll keep that as a rectangle, and then pick some point on that rectangle, evaluate the function at that point, and use that for the height. So instead of our function being some curvy, floppy surface, we just flatten it out above some small rectangle in the XY plane to calculate the volume, and then we integrate, which is just adding up all those rectangles. Well, rectangular solids. We want to apply the same thing when the floor is described in polar coordinates. We're going to take a small particular value of r and a particular value of theta, evaluate the function f at r theta to be the height, but then we need to multiply by the area. Here's the problem that we run into. R might be measured in a distance, but theta is measured in radians. Or degrees, I don't want to judge, but radians. Radians. That is the way. It's difficult for me. I also have a trig class, so I have to switch back and forth between radians and degrees. But y'all put your calculator in radians and leave it there. So theta is measured in radians. So if I multiply just d theta by dr, I don't get area. I just have length. So that's a problem. I need the d theta to be, I need the d theta to be a width, the way that I've labeled it here today. I need d theta to be measured, to be converted over into meters, so that when I multiply that width times the dr, I get area. And so my integral works out. I have the dA to be the area, and then I got my function to get the height. When I multiply those together, I get a volume. Then I add them all up and I get the volume under the surface and above the region in the XY plane. Any questions? This is why nobody likes math class. We can't just ask simple questions. It took me like 10 minutes to set up what the question is today and make sure everybody understands what the question is. Is everybody okay with the question? Okay. So there's one thing that we want to maybe notice, maybe that we've noticed, but that we want to not worry about. First of all, this little purple box that I've drawn here, you might notice that it has a curved side. So it's not quite a rectangle. And that may bother some of you. Does it bother you? Maybe it didn't bother you before, but now it does. But remember, this is calculus and we're looking at things that are very, very small. And if we look really close, it's not that curved. For all the rigor that we go through with this limits and the epsilons and the deltas, Michael, we're going to take this little box, which is a rectangle, even though it's not quite a rectangle, because it's close to being a rectangle. And then when people say, well, how close to a rectangle is it? Within epsilon, which means that if we just keep looking closer, it'll keep looking more and more like a little tiny box. So it's not quite a square, but it's close enough. That little orange side is curved. And that little orange side on the other side, a little bit farther away, that one's actually a little bit longer than the one inside. But if we make dr small enough, it won't be that much longer. And we can approximate this for the box. So the problem that we notice, is that d theta is not a length. So if this box is close to the origin, then this little orange leg, orange side is small. But because of the way angles work, the further we are from the origin, the longer that little orange side is going to be. So if we're down here close to the origin where r is very small, we've got this little tiny orange side. But out here where we're far away from the origin, that orange side is very large. Fortunately for our heroes, we know the circumference of a circle. And also, fortunately for our heroes, that this length that we're going to use for the r, that little curved piece, is proportional to how far we are from the origin. So to turn d theta into a width that we can use in an area calculation, we just need to calculate the arc length of that little orange side. So we're going to calculate arc length. We're going to use arc length to turn that orange side into a length. Spelled L wrong. The arc length is just going to be theta multiplied by r, where theta is in radians. Because of course it is. We already knew this because we know the circumference of a circle is 2 pi r. 2 pi is the angle going all the way around. So we multiply that by r. That gives us the circumference of the circle. So if we want a piece of that, we just take theta in radians and multiply by r. So secretly, we taught you the arc length formula when we taught you the circumference of a circle was 2 pi times the radius. That's just the arc length where theta is equal to 2 pi. So we're going to shrink this theta down to a very small d theta, and we just have to multiply by r. So to turn d theta into a width, we just multiply by r multiply d theta by r. That turns d theta into a width using the arc length. Then r d theta times the dr gives us an area. So now our integral does what we want it to do. The function is giving us the height. R times d theta times dr is giving us an area. Multiply those together, we get a volume. Everybody's happy. In the setup, that extra factor of r is part of the dA, but in the mechanics, that r gets integrated with the function. So it's part of the dA for the setup. It's part of the function that you have to integrate. So you're not just integrating the function, you're integrating r times the function. So that r is part of the dA in the setup, but now it's part of the function that you integrate. Let's grab our example from yesterday, if we can remember it. And by we, I mean me. So recall, we integrated this function, 9 minus the circle. Oh, 9 minus x squared plus y squared. 9 minus the sum of the square of x and the square of y. See, this is the problem in pointing out how badly we speak math. Now you become aware of it. And then you start worrying about saying things properly. Especially because my words speaking are getting translated into words typed. What if someone's just reading it without reading this part? I don't know. So we converted this to the function f of r theta as 9 minus r squared. The extra factor of r doesn't show up here. This is how we calculate the height. Now, when we set up the double integral, I need more space. When we set up the double integral, we had 9 minus r squared for our height. But it wasn't good enough to just have d theta times dr. We need this extra factor of r to be part of the d theta so that our dA is an area. So these three pieces are the area. And this function is still our height. I listed theta first, so d theta we were in the second quadrant, so that's from pi over 2 to pi. And we had a piece of a circle of radius 3, so r will go from 0 to 3. I need that extra factor of r to turn d theta into a width. So that we can make an area times height. When we go to integrate, I'm going to include the r with my height function, and that will be what we integrate. So I'm going to integrate the function 9r minus r cubed d theta dr. That r shows up because it turns the d theta into a width, but it gets included with the function for the integration. Any questions? Better way to write it. Now we're just integrating. At this point, we're seeing how valuable it was to switch to polar coordinates because we had so much round stuff going on. Remember, our integration at this point was trigonometric substitution. And we were like, oh, boo, even though that's the most fun integration technique. But here, we're just integrating polynomials. So you're like, oh, yay, even that's the most boring integration technique. We're also like, nice planning, dude. We don't have enough space to finish our integral. Being Friday, I should just bail on the rest of this integral, but you know, now I'm stuck. So I just got 9 pi minus 9 pi over 2. So I'm just gonna, this just says divide this by 2. So we're gonna have integral from 0 to 3 of 9/2 pi times r minus, so that one subtracts that one, but minus pi r cubed minus minus is plus pi over 2, so pi over 2. I subtract everything right. 9 minus 9/2 is 9/2 minus 1 plus a half minus a half. Wow, I think I actually did the arithmetic correctly. Still no trigonometric substitution because we took our round stuff and just made it a function, r. So now we can integrate with respect to r. We'll have 3 pi over 2. Oh, no, that's the next one. This one is the r squared. So 9 pi over 4 r squared. Minus, add 1, 4. So pi over 8 r to the 4th evaluated from 0 to 3. So this was super convenient converting to polar coordinates because we had all this circular stuff. We know that with circles, pi's need to show up, but if we're plugging in real numbers, we know that some sine inverses are going to have to show up. Because we're going to have to do some sine inverse of stuff to end up with pi. But when we use polar coordinates, we're just measuring angles in pi. The pi shows up during the setup. So it makes our life easier that way. Any questions? How's everybody okay? I've mentioned it before, but it bears repeating. There are 3 great tricks in mathematics. Add 0, multiply by 1, change your variables, which is just do a substitution. Those are the 3 great tricks of math, and that's the one that we did here. We looked at what we were dealing with, and we're like, oh, all this shit is round. Let's use polar coordinates. And look how much easier our calculations were. Meanwhile, there's a computer in the background. It's like, oh, I could have done that for you. I'm like, oh, shut up, computer. We're trying to understand stuff. Then the computer's like, oh, human curiosity is a detriment to understanding and efficiency. Humans must be destroyed. And then Skynet. Does everybody know who Skynet is? Has anybody seen Terminator? They keep trying to bring things back because the things that were movies and music and television shows when I was a teenager, now that I'm in my 50s and like everybody else that was a teenager at the same time I is in their 50s, they're at a higher position at the movie companies and the television studios. So they could say, you know what we should do? We should take the stuff that I liked when I was a teenager and make that. Kids will love it, Michael. They will know what you're talking about. No, it'll be fine. And then so we just make stuff that we want to make. You know what I mean? Think about the stuff that you were listening to and watching when you were 14. I know that wasn't very long ago for you. But when you're in your 40s, you're going to become so happy when it shows up on the radio. But you're going to realize that the radio is being played in the grocery store. Your music, which was so hip and cool when you were young, will become Muzak, just filling the background as you shop for your produce. This is the way. Any questions? Comment? Snijder. The main thing that I want to get across, why I keep saying it, is that one of our variables is an angle. So when I do d theta, theta is an angle. So when I write d theta, I'm not writing a length. I can't do length times width times height because d theta is not a width. I have to multiply by how far it is from the origin. In this case, the pole. How far it is from the pole to turn it into a length. But all we need is arc length. And all arc length is a piece of circumference of the circle. So we have all this stuff in place. It fits with the story, the through line of Calc 3. Calc 3 is not new, it's just adapting old, which fits the through line of math. Math is not new, it's just adapting old. You know what I mean? Everyone's like, oh, it's the new math. Like, well, there is no new math. All the stuff that old people don't understand about what they're calling new math is shit that we definitely tried to teach them when they were kids. But we emphasize the wrong stuff. And they think it's about process. They think we could just take math, break it up into these little chunks and just feed you these little bites. But that makes it way more difficult to put all the pieces together. And that's why math, the way we designed it, the way that we teach it, the way we hand it to people, it's like gatekeeping. We give you all these pieces, and instead of telling you how they fit together, we just hand you a bunch of pieces. We've taken math, we've broken it down into its constituent Legos and just handed you a pile of Legos. And then when you can't put it together, we say, you're bad at math. And the students, being children, when they first encounter math, don't know enough to say, dude, you haven't taught me how this goes together. You're just expecting me to know how it goes together. And the problem that we run into there is some kids just figure that shit out. Lucky them. They get to be put in the category of good at math. And not until we've acquired all this trauma linked to math do we realize that math is not magic. It's not some special skill. Math is an area of knowledge that anyone can acquire. Nobody in this room has anything physically stopping them from understanding math, like going on in your brain. I realize that there are things that are physically stopping you from going to school because that's the kind of society we decided to set up. But there's nothing physically stopping you in your brain from understanding this. Math wants one thing, your time and your attention. That's it. You spend the time paying attention and math will pay off. Not with dollars, but with understanding. That makes sense? And then we get annoyed because some people pick it up faster. And so in a room full of 40 students, I know we don't have 40 people here today, but we have some people here virtually. In a room full of 40 students, there's going to be one that can answer every single question. You're thinking, oh, why am I not that person? And you take that characteristic of that one student that does know what everything is and apply it to the other 39 people in the room. It's like, oh, I'm the only one that doesn't understand. Get over yourself. Most of the people in the room are not going to understand what the F I'm talking about. That's how we play the game. That's why I keep saying the same thing over and over again. Like d theta is not a length. We have to do something to turn it into a length so that dA can be an area. So I keep saying things over and over again. Integration is multiplication, but one of the factors is continuously variable. So integration is addition. But weird addition over a continuum, where do you put the pluses? That makes sense? How's everybody? Incorrect, by the way. If you're like, oh yeah, that makes sense. No, it doesn't. The whole point of going to school is that the shit doesn't make sense. But with time and attention and good habit, it can, it will. Any questions? When you're confused on your math homework, there's nothing wrong with you. When you forget stuff, there's nothing wrong with you. It's annoying as fuck. Because like, we just talked about this. Why doesn't it make sense? It made sense when I was sitting in the classroom. Keep in mind, when you're sitting in the classroom, who was doing the problem? That might be a contributing factor to why it made sense. And I don't get to follow y'all home and do your homework with you, right? Because that would be bad anyway. First of all, you don't want me in your house. That's weird. That you don't want to see me. You don't even want to see me somewhere other than campus. Like if I'm walking through the movie theater and you see me, like, no, this is weird. He's gonna give me a quiz or something. Or like I'm at your station in the restaurant. You're like, oh man, can someone switch stations with me? That's my math teacher. I'm not giving them food. You know what I mean? So anyway, it would be weird because also, as a teacher, I have a tendency to just kind of take over. And that's incorrect. I switch back to my tutoring days, my early tutoring days, before I figured out that I shouldn't just do the problems for people. And I just explain too much. You know what I mean? So here's the big thing. Once again, dA is dx times dy. Length times width is area. This is important because eventually this is going to be dx, dy, dz. Length times width times height is volume. Oh, well, I guess this is just going to be 4-dimensional volume. But the point of thinking of it that way is that when we switch to a different coordinate system, when instead of x and y, we have r and theta, changes in angle are not lengths. So they don't fit into our dA or our upgraded dV. We have to just use the arc length to convert our changes in angle to changes in length, width, or height. Any questions? How's everybody okay? All right, that's going to do it for today. That's going to do it for this week. I'll see y'all on Monday. Everybody have a good weekend and thanks for playing.